how do machines actually think? Or maybe how do they learn? Is it, some kind of digital magic? Or is it something we can actually get our heads around, maybe even replicate? Welcome to the deep dive. This is where we take complex topics, sometimes really complex ones, and we distill them down into the essential knowledge you need. Basically, a shortcut to being well informed. Today, we're diving deep into the fundamental ways machines learn. We'll be exploring the core ideas behind supervised, unsupervised, and reinforcement learning. And for this, we're drawing on some fascinating insights from Andrew Burkhoff's The 100-Page Machine Learning book, and also some really thought-provoking discussions with top AI architects, people like Andrew Ng, Jan LeCun, Demis Hassabis, and others featured in Martin Ford's book, Architects of Intelligence. Our mission today, simple. Unpack these core concepts in plain English. We want to highlight the surprising bits, the key insights, so you walk away with a really clear understanding of, well, the backbone of modern AI. So let's start right at the beginning. When we talk about machine learning, what are we really talking about?
Right. Well, at its heart, machine learning is really a branch of artificial intelligence. And it's all about creating algorithms, these sets of rules that can learn directly from data.
Learn from data. Okay.
Yeah, think of it like computer programs that kind of program themselves by looking at information. They're not explicitly coded for every single possibility, every task.
Huh. So it's moving beyond that old idea that, computers only do what they're programmed to do.
Exactly. That's a really good way to put it. They're finding patterns and making decisions based on the data they see.
So it's a bit like how humans learn from experience.
It is, yes, but in, let's say, very structured ways. There are lots of different types, but today we'll focus on the three big ones, the fundamental paradigms that really define how machines learn: supervised, unsupervised, and reinforcement learning.
Got it. Three core ways.
Each one tackles a different kind of learning problem, uses data differently.
Okay, let's unpack supervised learning first then. The name itself, supervised, it sounds like there's a guide involved, a teacher maybe. What does that guidance actually look like in practice?
That's a great intuition. In supervised learning, the guidance comes from something we call labeled data.
Labeled data?
Yeah, imagine you're teaching a kid, like different animals. You show them a picture of a cat and you say, this is a cat, right? You do that again and again with lots of pictures, always giving the correct label.
Okay, makes sense.
So in machine learning, you give the machine a data set where each input, maybe it's a photo, maybe an email, is already paired with the correct label, like cat for the photo or +1 for spam for the email.
Ah, so the answer is provided during training?
Precisely. The algorithm's goal then is to build a model, kind of like an internal set of rules or connections that can look at a new input, something it hasn't seen during training, and correctly figure out its label.
So this is how we get things like medical diagnosis predictions or spam filters, or even those systems that recognize faces or objects in photos, by feeding them tons of examples.
Exactly that. And Andrei Burkhoff, in the 100-Page Machine Learning book, he explains it really well. The machine isn't just like memorizing the answers. That wouldn't be very useful.
Right, because it needs to work on new things.
Exactly. It's actually solving a pretty sophisticated optimization problem. It's tweaking internal settings, these numbers we call parameters, adjusting them over and over until its predictions match the labeled examples it was trained on.
Like finding the perfect settings on some complex machine.
Kind of, yeah. Or think of it like finding the best possible dividing line, what we call a decision boundary, that separates, say, the spam emails from the not spam emails in your data.
Okay. And what are some of the main tools, the algorithms that actually do this separating?
Well, one really important one is the support vector machine, or SVM. The key idea, the sort of insight with SVMs, is they try to be really robust. They look for the widest possible gap or margin between the different types of data points.
Widest gap. Why does that help?
Because a wider gap means it's less likely to misclassify new points that fall near the boundary. It makes the model more resilient. And the boundary doesn't have to be a straight line. Using clever math tricks called kernels, it can be a curve, a plane, almost anything.
Interesting. What else?
Then you've got logistic regression. Now, the name is a bit confusing because it sounds like it's about numbers, but it's actually for classification, deciding between categories.
Right, like spam or not spam.
Exactly. It calculates the probability, the likelihood, of something belonging to a class based on its features. It maps the input to a probability between 0 and 1.
Okay. And you mentioned decision trees.
Yeah, algorithms like ID3 build decision trees. Think of it like a flowchart. The algorithm looks at the data and asks a series of questions based on the features like, is the sender address suspicious? Or does the email contain the word free? and each question splits the data.
Sorting it out step by step.
Exactly. It keeps splitting until it gets to groups that are mostly one type or another. It tries to make splits that reduce the mixed upness, the technical term is entropy, as much as possible at each step.
So all these methods find ways to draw lines or make rules based on the labeled training data? How does that help when a completely new, unseen email or photo comes along? Why does the model work then?
Good question. If the learning process worked well, and if the classes in your data are actually separable in some way, then the examples of each class end up living in different regions or subspaces defined by that decision boundary the algorithm found.
Okay.
So when a new example arrives, the model just figures out which region or subspace it falls into based on its features. And because that region is associated with a particular label, it makes the prediction.
And that's why you don't just test on the training data itself.
Absolutely crucial. We split the data, some for training the model, some for validating it during development, and a final chunk, the test set, that the model never sees until the very end. That tells us if it's truly learned to generalize, not just memorize. That's the goal. Good performance on unseen data.
That's really clever. But, I mean, it sounds almost too neat. I bet there are challenges, right? Some gotchas with supervised learning.
Oh, absolutely. You're spot on. Maybe the biggest surprising weakness, even for the really advanced deep learning models we hear about, is just how hungry they are for labeled data.
Yeah.
Perfectly labeled data.
Hungry for data.
Massively hungry. Andrew Ng, a big name in AI, often points this out as a major bottleneck for deep learning right now. And Yoshua Bengio, another pioneer, puts it starkly. He says, we can't realistically label everything in the world and meticulously explain every last detail to the computer. It's just impractical on a global scale.
Yeah, I can totally see how just getting all that labeled data would be a monumental task. What other headaches are there?
Another really big one is called overfitting. This is a classic problem. It's when the model learns the training data too well.
Too well? How can it learn too well?
It starts learning noise and irrelevant details, maybe statistical quirks, that are specific only to the training examples rather than the underlying pattern you actually care about.
Ah, like memorizing the answers for one specific test, but not understanding the subject.
Exactly like that. So Burkhoff gives an example. A car recognition system, trained only on pictures of, say, 10 specific cars, might completely fail when shown a slightly different model. Or maybe an animal detector learns that animals often appear against blurry backgrounds in the training photos, so it fails if the background is sharp.
So it learned the wrong cues.
Precisely. It picked up on irrelevant associations. The fixes involve things like using simpler models, or reducing the number of features the model looks at, or getting more diverse training data, or using techniques called regularization to kind of penalize complexity.
I've also heard that real-world data isn't exactly clean and tidy. It must be messy to work with.
Oh, incredibly messy. That's where data preprocessing becomes absolutely vital. Real data rarely comes ready to use. You might have categories like red, green, blue that need converting into numbers,
How do you do that?
often using something called one-hot encoding. Basically, you turn each category into its own binary feature, like a column for is red, is green, is blue, and then there's missing data. Values just aren't there.
What do you do then? Throw it out.
Sometimes you might have to remove the example if too much is missing. But often you use data imputation techniques to intelligently fill in the gaps, maybe using the average value for that feature or something more sophisticated.
Okay, so cleaning the data is a big job.
Huge. And then there's hyperparameter tuning.
Mm-hmm.
These algorithms often have important settings, knobs you need to dial in that aren't learned from the data itself. Things like a C value for SVMs or epsilon for decision trees.
And how do you choose those settings?
Mostly through experimentation, trying different values, seeing what works best on your validation data. Eric Horvitz and Demis Hassabis, both major figures, they describe getting top performance as almost like an art form, or even a kind of alchemy. It requires experience, intuition, sometimes called network whispering.
Wow, alchemy. So it's not just pure science yet.
There's definitely still a craft element to it.
Okay, and what about more fundamental issues? Like, do these systems truly understand what they're doing, or can they be easily tricked?
That hits on two really critical points, especially with modern deep learning. First, there's this surprising vulnerability to adversarial attacks.
Adversarial attacks. Sounds ominous.
It means that these systems, even ones that seem superhuman at tests like image recognition, can be completely fooled by tiny changes to the input changes a human wouldn't even notice.
Really? Like,
People have shown you can put special patterns on eyeglasses that make facial recognition systems misidentify the wearer. Or put small, specific stickers on a stop sign that make a self-driving car system classify it as something else entirely, like a speed limit sign.
Whoa, that's worrying for real-world use.
It is.
Yeah.
And it strongly suggests that whatever these networks are doing, it's very different from human perception. We aren't fooled by those tiny changes.
And in the second point, about understanding.
It's this lack of deeper understanding. Barbara Gross, another expert, she notes that these systems excel at statistical learning, pattern recognition, and large-scale data analysis. But crucially, they don't go below the surface,
Meaning?
meaning they often lack what we'd consider core aspects of intelligence, things like genuine common sense reasoning or understanding cause and effect or grasping nuance and context. They find correlations, but they don't necessarily understand why things are correlated.
Okay, so supervised learning, while powerful, clearly has limitations. The need for labeled data overfitting brittleness. That makes me think, is there a way for machines to learn without all that labeling? Is that where unsupervised learning comes in?
That's exactly the idea. Unsupervised learning tackles problems where your data set just doesn't have any labels. It's just raw data.
No teacher, no answer key.
Precisely. And that makes it incredibly exciting, right? You can imagine systems learning about the world just by observing it without humans needing to annotate everything.
Sure.
But it also makes it one of the really hard challenges in AI.
Why harder?
Because, as Burkhoff puts it, the absence of labels means the absence of a solid reference point to judge the quality of your model. You don't have that ground truth to compare against easily.
So if there are no labels to predict, what is the machine trying to learn? What's the goal?
It's fundamentally about finding hidden structure, discovering inherent patterns, groupings, or relationships within the data itself, without any prior guidance on what those patterns should be.
Finding structure, like what kind of structure?
Well, a really common task is clustering. The goal here is simply to group similar data points together, put the things that are alike into the same bucket, or cluster.
How does it know what's similar?
Different algorithms do it differently. A classic one is k-means. You sort of have to tell it how many clusters k you expect to find, maybe an educated guess. Then it iteratively assigns points to the nearest cluster center and recalculates those centers until things stabilize.
So you need to guess the number of groups first.
With k-means, yes. But there are other methods like dbScan or HDBScan, which are density-based. They don't need k. Instead, they look at how tightly packed the data points are. Points in dense regions become clusters, while points in sparse regions might be flagged as outliers, noise.
Ah, so they can find clusters of varying shapes and sizes and even spot unusual data points.
Exactly. Another approach is the Gaussian mixture model, GMM. It's a bit like k-means, but it assumes the clusters are, well, Gaussian distributions, bell curves, and it assigns points to clusters with probabilities, a soft assignment, rather than a hard yes-no.
So basically finding hidden groups in the data that maybe we wouldn't have spotted ourselves.
That's a big part of it. Another key area is dimensionality reduction.
Dimensionality reduction. Sounds technical.
It just means reducing the number of features or dimensions for each data point. Imagine you have data with hundreds of characteristics for each item. That's hard to analyze and especially hard to visualize.
Right, we can only really see in 2D or 3D.
Exactly. Techniques like principal component analysis, PCA, find ways to combine the original features into a smaller set of new features, called principal components, that capture most of the important variation in the data. While modern algorithms can often handle high dimensions directly, PCA is still super useful for data visualization. It lets us plot complex data in 2D or 3D so we can see the patterns.
Okay, that makes sense for helping us humans grasp complex data, but can unsupervised learning do something more abstract, like understanding language, maybe?
Absolutely. And that leads to one of the most fascinating applications, word embedding, particularly techniques like word-to-vec.
Word embedding, putting words into vectors.
Essentially, yes. The goal is to represent each word as a list of numbers, a vector in a high-dimensional space. Think of it like giving every word an address in a giant city.
An address.
Yeah, and the key idea is that words with similar meanings, or words that tend to appear in similar contexts in large amounts of text, end up with addresses that are close to each other in this city.
So book, paper, article would live in the same neighborhood.
Pretty much. The machine learns this automatically just by looking at which words co-occur in millions of sentences. It discovers semantic relationships purely from statistical patterns in language data.
That's incredible. Does it allow for anything else?
It allows for really cool analogies using simple vector math. The classic example is if you take the vector for king, Subtract the vector for man and add the vector for woman, the resulting vector is closest to the vector for queen.
Wow. So king man plus woman, queen, just using these word addresses?
Basically, yes, it captures relational similarities. It's a powerful demonstration of unsupervised learning, uncovering deep structure in language.
Amazing. So it really sounds like unsupervised learning is potentially a huge piece of the puzzle for more advanced AI.
Many researchers think so.
Yeah.
Yoshua Bengio calls it the key to learning enough background knowledge about the world so that common sense will emerge. If we could get machines to learn efficiently in a truly unsupervised way, just by observing, that would likely be one of the biggest breakthroughs in AI, a major step, an important waypoint on the road to human-level AI.
Okay, so we've got supervised learning with its labeled data, its teacher. We've got unsupervised learning finding patterns on its own. What about the third one, reinforcement learning? If supervised is the teacher and unsupervised is self-study, what's this one? Is it like learning through consequences, trial and error?
That's a fantastic analogy. Yes, reinforcement learning, RL, is very much inspired by how animals, including us, learn through trial and error, through consequences. Think operant conditioning from psychology.
Operant conditioning, Skinner boxes and rats pressing levers.
Kind of. In RL, you have an agent, like a robot, or a program controlling a game character acting within an environment, which is often a computer simulation.
Mm.
The agent performs actions,
Mm.
and occasionally, based on the outcome of its actions, it receives a reward, or maybe a penalty, a signal telling it if it did something good or bad towards achieving some goal.
So no labeled data showing the right action for every step.
Nope. Just these intermittent reward signals. That's the only feedback the agent gets to learn from. It has to figure out, through trying things, which sequences of actions lead to the biggest cumulative reward over time.
Can you give us a more concrete example of how that works, that trial and error process?
Sure. Let's use Burkhoff's example.
Mm-hmm.
Imagine a simple robot dog, let's call it Rosie, learning to kick a ball. Initially, Rosie just moves randomly, flails around maybe.
Right, doesn't know what to do.
Exactly. But suppose one of her random actions, maybe moving forward, when she happens to be one step away from the ball, puts her in a position where she can kick it. And if kicking, it gives her a positive reward.
Uh-huh. She gets a gold star, basically.
Sort of. That positive feedback reinforces the action forward, taken in that state, one step away. The system often uses something called a Q table. Think of it like a big cheat sheet the agent builds over time.
A Q table.
It stores, for every possible state the agent can be in, an estimate of the future reward it expects to get if it takes a specific action from that state. It starts as random guesses.
And it gets better.
Yes, as Rosie tries actions and gets rewards, or penalties, she updates the values in the Q table. An action that leads to a reward gets its Q value increased for that state. It's learning, as Burkhoff says, a guess from a better guess, constantly refining its expectations based on experience.
Like slowly figuring out the best moves in a game.
Exactly. It's like learning to ride a bike. You don't get explicit instructions for every tiny muscle movement. You try things, you fall, negative feedback, you adjust, and eventually you figure out the sequence of actions that keeps you balanced and moving forward. Positive feedback.
And this immediately makes me think of those huge AI successes in games. DeepMind's AlphaGo beating world champions at Go. Was that reinforcement learning?
That was a landmark achievement driven by reinforcement learning, yes. Especially the later version, AlphaGo Zero and AlphaZero.
What was special about them?
They demonstrated the power of pure reinforcement learning. AlphaZero learned to play Go, chess, and shogi at a superhuman level, starting with only the rules of the game. No human games and no human strategies fed into it initially.
Just played itself.
Millions and millions of times. It learned entirely through self-play, refining its strategies based on winning or losing against itself. It learned to reason better from experience, discovering strategies humans hadn't even conceived of. And as Dimas Hassabis, DeepMind's co-founder, often emphasizes, games are just our training domain. The goal isn't just to solve games, it's to develop these powerful general learning algorithms that can then be applied to real-world problems like science, medicine, energy.
Okay, so if it's that powerful in complex games, why aren't we just using RL to teach, say, self-driving cars to drive perfectly by just letting them practice in simulation or even the real world?
Well, applying RL effectively to complex, messy, real-world problems faces some major stumbling blocks. It's not quite as simple as just letting it loose.
What kind of stumbling blocks?
First, there's the sheer complexity of the real world, the problem of infinite states. Remember that Q table? Mapping states to action values.
Yeah, the cheat sheet.
Well, for a task like driving in a busy city, the number of possible states, based on everything the car sees from cameras, LiDAR, radar, its own speed, position, etc., is practically infinite. You can't make a lookup table that big.
So how do they handle that?
Modern approaches don't use simple tables. They use deep neural networks to approximate the Q values, or to directly learn a policy, which action to take in a given state. These networks can handle incredibly complex, high-dimensional inputs, but training them effectively is still hard.
Okay, that makes sense.
What else? Another huge challenge is defining the reward function. How do you specify exactly what constitutes good driving in terms of numerical rewards and penalties for every possible micro situation?
Right. You want it to be safe, efficient, smooth, follow the rules, but also maybe be courteous. How do you put a number on courteous?
Exactly. Getting that reward signal right is incredibly difficult and critical. A poorly designed reward can lead to unexpected and undesirable behaviors as the agent optimizes for that specific signal, even if it violates common sense.
And any other big limitations?
Yes, a really significant one is the issue of superficiality and lack of transfer. RL solutions, especially those learned in simulation, can sometimes be surprisingly brittle or superficial.
What do you mean by superficial?
For example, an RL system trained to play the old Atari game Breakout might achieve superhuman scores. But researchers found that if you just shifted the paddle's position on the screen by a few pixels, something a human player would adapt to instantly get out of the battle, the AI's performance could completely collapse.
Because it hadn't learned the concept of hitting the ball with the paddle, just this specific pixel pattern?
Something like that. It learned a strategy tightly coupled to the exact training conditions. Similarly, AlphaGo mastered the standard 19 by 19 Go board, but it couldn't immediately apply that skill to, say, a 17 by 17 board without significant retraining and potentially restructuring.
So it doesn't generalize well.
It struggles with what we call abstraction, domain generalization, or transfer learning. Humans are amazing at taking knowledge learned in one situation and applying it flexibly to a new, even quite different situation. That ability to transfer learning is still a major hurdle for current AI, including RL.
Okay, so we've covered a lot of ground. Supervised learning, learning from labeled examples with a teacher, unsupervised, finding patterns in raw data on its own, and reinforcement learning, learning through trial, error, and rewards. These are the big three. Stepping back, what does this all mean for the bigger picture of AI? Where does it leave us?
Well, these three paradigms really form the bedrock of modern machine learning, and machine learning in turn is what's fueling this huge AI revolution we're seeing.
And deep learning fits in here how?
Deep learning, which has driven so many recent breakthroughs, think image recognition, amazing language translation, facial recognition, is primarily, though not exclusively, a very powerful set of techniques within the supervised learning paradigm. But it's crucial to remember what many experts keep stressing. Deep learning is just one tool in the toolbox.
Right. It's incredibly powerful for certain things, but it's not the whole story of intelligence.
Exactly. Achieving truly flexible, adaptable, human-level AI, or artificial general intelligence, AGI, if you like, that's likely going to require much more. It'll probably need deep integration of ideas from all these learning paradigms, plus potentially new ones, and insights from other areas of AI and cognitive science.
So it's not just about feeding current systems more data or giving them faster computers. There are fundamental gaps.
Precisely. There are still huge, fundamental challenges that remain largely unsolved. One big one is common sense reasoning.
Common sense.
Yeah, the basic understanding of how the world works that humans just have. Oren Etzioni, another AI leader, points out that this idea of emergent intelligence, that deep understanding will just magically appear if you feed systems enough data, well, that's not what we've seen so far. Machines still struggle with simple common sense inferences.
Like the example you mentioned earlier about the plant needing sunlight.
Exactly, or countless other things. Then there's causal reasoning understanding, not just that A and B happen together, but that A causes B. Judea Pearl has done foundational work here, arguing it's absolutely critical for real intelligence.
And what about truly understanding nuance, especially in something like human language?
That's another huge area. Current systems, especially large language models, are amazing at generating fluent text because they've learned statistical patterns from vast data sets. But as Barbara Gross said, they often don't go below the surface. They struggle with genuine understanding of intent, context, ambiguity, subtext, all the things that make human communication rich.
And the transfer learning issue we talked about with RL.
That remains a major challenge across the board. That human ability to take knowledge from one domain and apply it creatively to a completely novel one, that's something AI is still far from achieving reliably.
So the path forward isn't just scaling up current methods, it's about fundamental breakthroughs.
That seems to be the consensus among many leading researchers. The field is actively working on all these hard problems. The long-term vision isn't just about building narrow AI applications that do one task well. It's about creating systems that are, to use a collection of descriptive terms, holistic, contextualized, situationally aware, nuanced, multifaceted, and multidimensional.
Systems that learn more like humans do.
Perhaps systems that learn effectively not just from massive labeled data sets, supervised, but also through observation, unsupervised, through interaction, reinforcement, and maybe through other forms of learning we don't even fully understand yet.
Yeah.
Building intelligence that can adapt, reason, and understand the world in a much richer, more flexible way.
Wow. What an incredible deep dive into the ways machines learn. From supervised learning, needing that labeled data, to unsupervised finding hidden patterns, and reinforcement learning, mastering tasks through trial and error. It's really clear that AI is built on this fascinating, diverse foundation.
It really is. And we've seen just how powerful these different approaches can be for specific kinds of problems. The progress is undeniable. But yeah, we've also touched on those profound gaps, the differences between how machines currently learn and how humans seem to acquire knowledge, that nuanced, contextual, almost intuitive understanding we have.
Well, thank you for guiding us through that. We really hope that you, listening, are walking away with a clearer picture of both the amazing capabilities of machine learning today and also the really exciting, difficult challenges that still lie ahead on the path to more general AI.
And maybe here's a final thought to leave you with. If these machine learning models are getting so good at essentially self-programming based on data, and even learning by refining guesses, learning a guess from a better guess, as
Yeah.
Burkhoff puts it, what does that imply about our own learning processes? Are we humans also, in some sense, just incredibly complex optimization machines running algorithms honed by evolution? Or is there something fundamentally different about our consciousness, our innate curiosity, our ability to abstract and reason that truly sets us apart?
Something to definitely mull over until our next deep dive.